Hi. In this problem, we are going to look at a question in combinatorics, and this will lead us to the idea of Stirling numbers. So let's look at the problem. If there must be at least one person on each table, in how many ways can six people be seated around two tables, right? A pretty simple problem. The way we do it is we group the six people into different groups of how many people go on one table and how many go on the other table, right? So you can say case one will be if there are two tables, we can group them as 5 and 1. So 5 people go on one table and one person goes on the other table because no table can be empty, right? So when we divide them into groups of 5 and 1, you can select this one person in 6C1 ways. Once you have selected this one person, this person goes on one table and the other 5 on the other table. So the number of ways of arranging people around a table for n people, it is n minus 1 factorial. That is something that you guys might be aware of. So the number of ways of doing this would be 6C1 times. For the 5 people, it will be 4 factorial. And for the one person, it will be 0 factorial. So that is 1. So this comes out to basically 144, right? Then case 2 is when we have 4 people on one table and 2 on the other. So again, we will do it in 6C2 ways. We'll select the 2 people that go on one and the remaining 4 go on the other. So the total number would be 6C2 multiplied by 3 factorial multiplied by 1 factorial. Because 3 factorial is the number of ways of arranging these 4 people on one table. And 1 factorial is the number of ways of arranging these 2 people on one table, right? So this comes out to be basically 15 into 6, which is 90, right? And finally, case 3, where you have 3 plus 3. So here we have to be a little careful because when you select 6C3 ways of selecting 3, the other 3 go on the other table. But this arrangement has a little bit of symmetry. Like you could have done the same thing if you put 3 people here, the remaining 3 people go here. So the actual number of ways will be half because we can arrange the 2 tables amongst themselves because they have equal people in this group. So since there are 2 groups with equal number of people, we can arrange the 2 groups in 2 factorial ways. So we have to divide that because that will not be identical. So this way comes out to be half into 6C3, and then you have to do 2 factorial into 2 factorial to arrange the people on that table, right? If you're not convinced by this, you need to take examples. So for example, if I take 2 tables and I have 6 people, so A, B, C, D, E, F, A, B, C, and D, E, F. So instead of having 6C3 or 20 ways, actually there will be only 10 ways to group them in 3 ways, in groups of 3 and 3. You can list out all the arrangements. You can say A, B, C, D, E, F is one grouping. Then another grouping is A, C, D, B, E, F. And just try to list it down. You will find that there are not 20, which is 6C3, but there's actually only 10 ways to divide them into groups of 3 and 3. So this total number comes out to be basically 40, right? So 10 into 4, so it is 40. So the total number of ways to do this problem, 6 people arranged in around 2 tables, such that no table is empty, will come out to be basically 144 plus 90 plus 40 by the addition principle. And this comes out to be 274 ways. If we do a slightly different problem now, if we have 3 tables, for example, and we have 6 people, again, we will do it in the same way. Case 1 would be the case of 4 plus 1 plus 1. And this grouping can be done in 6C4. And then there are 2 groups of the same size. So we'll divide by 2 factorial. And then we'll arrange it in 3 factorial into 0 factorial into 0 factorial ways. So this comes out to be 90. And case 2 would be 3 plus 2 plus 1. Now there are all the groups are unequal sized groups, right? So we just do 6C3 to select 3 people for this table, and then remaining 3 people we do 3C2 for the second table, and remaining person is the one person left. So that is only one way. And after that we do 2 factorial into 1 factorial, which comes out to be 120. And case 3 which is 2 plus 2 plus 2, groups of 2, and there are 3 equal groups, right? So we'll say 6C2, 4C2, but we'll have to divide by 3 factorial here because there are 3 groups which are equal member groups, right? And then we multiply by 1 factorial to arrange the people on those tables. So this comes out to be 15. So in the case of 3 tables and 6 people, the total answer would be 90 plus 120 plus 15, which comes out to be 225. Now, this is a very general class of problems, and we will discover a pattern here. So we'll actually define something called Stirling numbers. So we'll say, given R and N belong to integers with 0 less than equal to N and N is less than equal to R, right? We will define S of Rn to be the number of ways to arrange R distinct people or objects around n identical circles, such that each circle has at least one object. Correct. Now, this type of numbers, this number of ways is basically called Stirling numbers of the first kind. And so far, with the 2 problems that we have solved, we have found the values of S62, which was 274, 6 people around 2 tables. And we also found S63, which was 225, which is 6 people around 3 tables, right? Now, let's look at some of the properties of these Stirling numbers. There are some obvious properties that I will not prove, but I will just state them so that you can understand the properties. You can convince yourself that this is true. So SR0 is 0. So basically R people around 0 tables. There is no way to do it, right? Then SRR is simply 1 because R people around R tables and each table has to be not empty. So each table can have only 1. So there is only one way to do that, right? Then you have SR of 1. So R people around 1 table. So that will be obviously R minus 1 factorial. We know that already, right? And you can also do this. SR R minus 1 will be RC2. Why? There are people around R minus 1 tables. So obviously 1 table has to have 2 people, right? 1 table has to have 2 people. So how many ways of selecting those 2 people from the R people? We can select those 2 people in RC2 ways. Once you have selected them, you have to put them on 1 table and the rest can be fit on all the remaining R minus 1 tables, right? R minus 2 tables, and everyone gets 1 person, right? So this is RC2. You can check a few small cases and you'll realize that that is true, right? Finally, we have this nice recursion, which I will prove. So SR of n will be equal to S of R minus 1, n minus 1, plus R minus 1 multiplied by S of R minus 1, comma n, right? Where n is less than equal to R, right? So this is a recursion that helps us to calculate higher values of S using lower values of S. So SRFN is related to S of R minus 1, N minus 1 and S of R minus 1, N, right? So let's understand this recursion because this will immediately help us calculate S63, S62 directly using lower values of S, right? So for example, if S62 had to be calculated, we would say that that is equal to S51 plus R is 6. So R minus 1 is 5 times S of R 5 and 2, right? Now you need S of 5, 2. Again, you will apply the same recursion again and you will get a lower value. And S51 is simple. S51 is simply 5 minus 1 factorial, right? So you just need to find S52 and then you will apply the recursion again. So this formula will be very useful if you want to calculate the problem in a general case and you have higher number of tables where case work might become very annoying, right? So how to prove this formula? So let's write the formula here. SR of n is equal to S of R minus 1, n minus 1, R minus 1, n minus 1 plus R minus 1 multiplied by S of R minus 1 comma m, right? So let's think about how to prove this one. So we'll denote the R objects with numbers with 1, 2, 3 till R, right? These are the R objects and we'll consider object 1. Consider object 1. Correct? Now there are two cases. In any arrangement of the objects, there are two mutually exclusive cases. Case 1 is when 1 is the only object in a circle. 1 is the only object in a circle. And the second case is where 1 is mixed with others in a circle, right? Okay, so let's think about these two mutually exclusive scenarios. And when 1 is the only object in a circle, then that means that one of the circles has just 1 and the remaining circles will have the rest of the things, right? So the number of remaining circles is n minus 1 circles and the number of remaining objects is R minus 1 objects. So obviously the R minus 1 objects have to be put in n minus 1 circles in this case and the last circle has just 1, right? So the number of ways to do that will be simply S of n minus 1, S of R minus 1, n minus 1, right? That is the definition of our Stirling number. So the number of ways to do this case 1 is simply S of R minus 1, n minus 1, right? Now we'll consider this case 2 where R minus 1 objects. In case 2, basically 1 is mixed with other objects in a circle, right? So think about it. The R minus 1 objects have to be placed on n circles. The total number of circles was n. So this can be done in SR minus 1 comma n ways. SR minus 1 comma n ways, because that is the definition of our Stirling numbers. And now one has to be placed on any of these circles. One has to be placed on some of these circles. And how many spaces are there? You can say that for each of the objects, you can put one to the immediate right of the corresponding object, right? So there are how many objects available? There are R minus 1 objects and you can put one anywhere. There is no restriction. You can put one anywhere beside any of these objects. So there are how many places? There are R minus 1 places, right? Where you can put one to the immediate right of any of the other objects, right? So the total number of ways to do this, to place one, is going to be R minus 1 times S of R minus 1 comma n, right? So this count is coming out to be R minus 1 into S of R minus 1 comma n. And the earlier count was S of R minus 1 comma n minus 1. So that gives us, by addition principle, because these are two mutually exclusive ways, that gives us this formula, right? S of R of n is equal to S of R minus 1 n minus 1 plus R minus 1 times S of R minus 1 comma n. Now, what is the utility of the formula? Now, you can solve simple cases like suppose you have 3 people and 2 tables, right? S of 3, 2. That will become basically S of 2, 1 plus 2 times S of, this will be 2, 2, right? Now, S of 2, 1 will be 2 objects on one circle. So that is simply 1 factorial plus 2 times S of 2, 2 is going to be simply one way, right? Because we know that S of R is 1, right? So you will see that there are 3 ways to do it. there are three ways to do it, and you can easily verify that that is true. You have three objects to be placed on two circles. So you can put A and B here, and you can put C here, or you can put B and C here, B and C here, and A here, or you can put C and A here, or B here, right? And since the circles were identical, that's the total number of ways possible, the three ways, right? Correct. So we are getting the correct expression for S32 from here. You can confirm once you have S32, you can get a higher value. You can get S42, right? S42 would be what? It will be S31 plus 3 times S of 32, right? S31 will be 2 factorial plus 3 times S of 32 is 9. So this is 9 plus 2, 11. So S42 is 11. And similarly, you can build up all the Stirling numbers using this recursion formula for small values of R and N. Now, obviously, that's not all. And later in future videos, what we will see is different kinds of Stirling numbers also. Stirling numbers of the second kind, which are also solving a class of problems that is very common in Olympiads and all. So I'll be making further videos on this topic. But for now, what we have done is we have solved a particular problem, the problem of arranging n objects on R circles, where each circle has to have at least one object. And we have generalized the problem and introduced these Stirling numbers. So hopefully you will be able to use the properties of Stirling numbers and solve such problems pretty easily. If you like the content, please subscribe to the channel, share the link with your friends, and I'll see you in the next video. Stay tuned for more combinatorics questions and more problems like these. See you next time.